It is a pleasure to introduce Vincent Pilloni from École Normale Supérieure de Lyon. And his title is Higher Coleman Theory, Part 1. Vincent.
Bonjour à tout le monde. So, hello, everybody. Okay, so I want to thank you for the invitation, and also I should have been in Montreal, and especially Henri and Adrian made lots of efforts so that I can come with my family, but it was not possible, so I'm sorry about this. Okay, so I'm going to share my screen. I mean, I hope. Okay. So this talk is, so this talk is so the oops, very slow. No, it's fine. So the title is Higher Coleman Theory. Okay, and so this is a joint work with George Boxer. Okay, and he will give a second talk right after this one on the same subject. Okay, so there are some notes which are available. Okay, so let me start. So the theme of this work is the current cohomology of Shimoa varieties, but let me start with a toy model. And so the toy model is the cohomology of a flag variety. So this is B over G. Okay, so let's fix G, which is split reductive over some field K. Okay, and then I pick a torus inside the Borel. And I denote by FL the quotient B over G, so the flag variety. So now, okay, I have the Weil group, and there is a length function from the Weil group to 0 D, which is the diagonal. Okay. Okay. Now, each time I pick some character of the torus, I get some G equivalent line bundle. Line bundle. On the flag variety. Okay, and let me normalize this in such a way that when K is in the dominant chamber, then this A0 of LK contains some IS. So that's how I've normalized this. All right. So now there's this classical result, which is the Borel-Weilbot theorem. Okay, and so this classical result tells the following. So it holds in characteristic 0, and it says that we have the two possibilities. So either. So the first possibility is that there are no elements in the Weil group such that W applied to G regular. Okay, and then the cohomology entirely vanishes. Okay. Or second possibility, there exists a unique element. Sorry, it's not kappa. Sorry, it's this action. So the dotted action. Or otherwise, there exists a unique element W such that W dot kappa is G regular. No, sorry, it's okay. No, sorry, it was correct. It's regular. So such that the W dot kappa is regular, and then in this case, the cohomology is concentrated in 1 degree. So it's really concentrated in the degree, the length of this element. So it vanishes in all the other degrees. And moreover, this is a highest weight W dot kappa representation. Okay, so it's also identified as a G model. Okay, all right. So let me. So really, this theorem is really about the position of kappa in the, I mean, with respect to the vial, to the chambers. Okay. Okay, and so also this theorem is a bit reminiscent of things we know about Shimoda varieties, except that the statement is much cleaner in some sense. But there are lots of things we'd like to prove for Shimoda varieties. So for Shimoda varieties, we also have automorphic sheaves indexed by weights, and we'd like to prove vanishing theorems, and also sometimes we like to have symmetries between the cohomology groups, like in this point too. Okay. Which go way beyond the Serre duality, right? I mean, this symmetry is very, I mean, is much more interesting and much stronger than Serre duality. Okay, it's all right. So let me briefly sketch a proof, because this is I mean, we're going to use these ideas later. So let me just sketch a proof according to Kempf. There are different ways to prove this, but yeah, here's the sketch. So we consider a stratification of the flag variety. So ZD, well, so what is ZI? So ZI is a union of Schubert cells. Okay, so this will be the union of all W, such that the length of W is equal to D minus I, okay, of these Schubert cells, which are the closure of B orbits of W. Okay, so this is a B equivariant stratification. And now there is a spectral sequence. So you see, each time you have a stratified space, there is a spectral sequence which computes the cohomology according to the stratification. Okay, and so the spectral sequence writes that way. So HP, ZP over ZP plus 1. So this is some local cohomology. And this to the cohomology. Sorry. Wait, no, sorry, what am I writing there? Sorry, this is. What did I write? And this converges to. Okay. So there is a spectral sequence like this. So I have to tell you what are these groups. So this is some local cohomology. And so these groups, so this R gamma ZP over ZP plus 1, this cohomology, it's a notation that is standard, but it means the cohomology we support in ZP minus ZP plus 1, which is a union of Brouillard cells of codimension P, of the flag variety minus ZP plus 1. So this is some open in the flag variety and with value in the open. Okay, so this is this cohomology. So now, I mean, if we write the spectral sequence, so on the E1 page, it looks like this. So you have A0, Z0 over Z1, and let me not write the, I mean, let me not write either the space of or the sheaf. I mean, it's obvious from the context. H1, Z1 over Z2, okay, H2, Z2 over Z3, etc. And then there are, so these are the differentials, but here you have also some, I mean, by spectral sequence, you have some H1, Z0 over Z1, etc. And it continues, and there you also have some H0, Z1 over Z2, etc. You have some H2, okay, Z1 over Z2. So you can imagine, right? But now there's something that is that somehow that there is a strong vanishing. So most of the term collapse in the spectral sequence, and what remains is just a complex. Okay, So what remains is just this complex, which computes the cohomology. So let's call this, I mean, that's the way it's called, it's the Cousin complex. Okay. So, I mean, this vanishing is not really deep. I mean, it's some easy computation in local cohomology. Okay. I will say a word in a second. Okay. And so we get an explicit complex which computes the cohomology. So what are the properties of this complex? So at first glance, it's a bit, I mean, it's a bit scary because we want to compute the cohomology, and the cohomology is going to be finite. But this is a cohomology of, I mean, these complexes, these modules, they are infinite dimensional K-vector spaces. Okay, so this is a bit scary. Nevertheless, they have explicit T action. Okay, so it's a complex. I mean, it was obtained using a B invariant stratification, and therefore we have a T action. And this action is completely explicit. Okay, so somehow we know the character of T on all these modules. Okay, so this is quite good. And well, even if the stratification was not G invariant, there are still some kind of some infinitesimal action. So some G hat action. And actually, it's a complex. The complex is in the BGG category O. Okay. All right. So let me just do an example so that this becomes, I mean, so that we get some intuition on this. Okay. So let's consider the easy case of P1, which is B divided by SL2. Okay. Okay, so now what's the stratification I'm considering? So now there are only two terms in the stratification. So I have the open, okay, which is Z0 minus Z1, and this will be just the affine space. And then I have the closed stratum, and this will be the point at infinity. Okay. And so now what's the Cousin complex? Well, this is just the cohomology of A1 with value in this sheaf, LK. And then you go to the cohomology, the H1 we support at infinity of P1 with value in LK. Okay, so that's the complex, right? And there you see that somehow all the other terms in the spectral sequence are going to vanish because A1 is affine, and so it has no higher cohomology. And on the other end, if you look at the cohomology we support in P1, then it has no H0, right? So here you get, you see where the vanishing comes from, right? So now we can, I mean, these are sheaves, right? But they are actually trivial either on A1 or on the neighborhood of the infinity. And therefore, this cohomology, it just looks like K, okay, which is the coordinate ring on A1 times some basis element. And this is going to go to, well, the cohomology we support in infinity of P1, this is the Laurent tails at infinity. So this is Kx minus 1 divided by Kx minus 1. Okay, so x minus 1 is the coordinate at infinity, and then you have some vector basis F. All right. So, and now let's look at weights. So the weights there, I mean, I claimed, so somehow, I mean, there was the weight of K, so the weight K, so the sheaf has some weight, and also the coordinate X is acted on, and therefore it has some weight. So in my convention, X will have minus 2. And so if I look at the weights, the weight of E will be K, and therefore, and since I'm telling you that the weight of X is minus 2, then I see that the weights are K minus 4, etc. And on the other side, the weight of F will be minus K, and therefore there the weight will be 2 minus K, minus 2 minus K, minus 4 minus K, and so on. So these are the weights. Okay, good. Right. So actually, I mean, with a little bit more work, one can see that this is actually, I mean, depending on K, this is actually either the dual BGG resolution or the BGG resolution of the highest weight vector of the highest weight representation of weight, either K or minus 2 minus K. All right. So now it's general phenomena that general that the weight of T on this Cousin complex, so on the HP ZP over ZP plus 1, are bounded below. So they are, sorry, they are bounded above. So they are, they are bounded, well, yeah, bounded above, like this. So they are less than W dot kappa, where the length of W is equal to P. Okay, so which is the phenomenon. So somehow you see that we have this complex, and like the behavior of the weight is quite different on each terms of this complex. So in particular, I mean, now I'm almost finished with this introduction. So now, given kappa, we can associate this set that I call C of kappa. And this is actually the set of elements in the Weil group, such that in some sense, the weights of the corresponding local cohomology in the Cousin complex, so according to W, so which means that this guy is dominant. W kappa plus rho is dominant. Okay, so this C of kappa is reduced to one element if and only if K was G regular, and in general, there can be more. I mean, there can be more elements. And now we can define like the big weight part of kappa, of the cohomology. So this is the big weight part, direct factor of the total cohomology, where somehow the weights, where here the weights are strictly greater than W dot kappa for all W which are not in this set C of kappa. Okay, so this is somehow, I mean, yeah. So I'm just keeping the subcomplex where the weight is kind of as big as possible. And now it really follows that by applying this big weight in the complex, and so I have this proposition that now this big weight part is now, it is in degrees. It is in degrees in the interval, sorry, degrees in the interval. So the infimum of the, sorry, for kappa, in C of kappa of the length, sorry, for W in C of kappa of the length of W and the maximum of the length of W for W in C of kappa. Okay, right. So I mean, so let me say that, I mean, this is a very easy result in some sense, and it's valid in all characteristics. Okay, whereas the Borel-Weilbot theorem is only valid in characteristic 0. Okay, and actually with more work, one can, in characteristic 0, it's also possible, I mean, using this kind of ideas to derive a full proof of the Borel-Weilbot theorem using properties of the category O. But at least there we have, I mean, the statement is not very hard, but somehow it gives a result which is valid in all characteristics. Okay, all right. So now the goal is to do the same thing with Shimura varieties. Okay, so that's the second part of the, and this is the complex of Shimura variety. So what I want to explain is this. So I want to explain that there is, sorry, it's very bad writing, there is a Cousin complex. The finite slope part of coherent cohomology. Okay, so I want to explain this, and then, okay, I think then I will give applications of this. Okay, so I need to quickly like introduce some notation. Okay, so let's so we take some Shimura datum, Gx. Okay. Okay, so now if we have a, okay, let me also fix a prime. Okay. I mean, now there will be a prime. Let's take K a compact open then we have some Shimura variety of level K attached to this data. Okay. And well, it has a toroidal compactification for some auxiliary choice. Okay. So we also have, I mean, for example, this was explained in Koski-Virta's talk. We have a parabolic P mu, okay, inside G, or maybe GC, but it doesn't really matter. So this is a parabolic attached to this data, and it has a Levy quotient, which I denote by mu. I think it was denoted L by L in Koski-Virta's talk. And then I have a functor from the representations of mu to vector bundles over this toroidal compactification. Okay. Right. Okay. Also, I will denote by D, which is the boundary. Right. All right. So this is very standard notation. Okay. And so what's of interest? So let me also fix a Borel, which is inside P mu. Right. So actually, for the experts, my P mu is the opposite of the P mu of Koski-Virta's talk. And this is why my weights, I mean, somehow modular forms will have positive weights. So then I take a Borel inside P mu and then a torus inside. Okay, right, so this is good. Okay, and therefore, now if I have some kappa, which is mu dominant, okay, so some character which is mu dominant, then I get a sheaf, which, so these are our sheaves of, I mean, our automorphic vector bundles. Okay, very good. So, okay, and so now what are the objects of interest? So let me, okay, yes. So the objects of interest are these cohomologies. Okay, so the toroidal compactifications. So the cohomology of nu kappa. You also have the cohomology, the cuspidal cohomology. Okay, and it turns out, well, that when the Shimura variety is not compact, you kind of get better result by considering the interior cohomology, which in some sense kills the cohomology of the boundary. And so, okay, so this is the interior cohomology. And this interior cohomology is the image of the cuspidal cohomology into the usual cohomology. So this is the image of cuspidal cohomology. Okay. All right. So these are like the cohomologies of interest for us. Okay, so now I need to make some assumptions. So, okay, and so this assumption will be there till the end of the talk. So I assume that Gx is abelian. Okay, so this. Okay, so this includes, for example, the Ziegel datum or the Hilbert datum, if you like. GQP is split. Sorry, it's quasi-split. Okay, and I think that's all. Okay, so now, okay, I need one more piece of notation, which is, so you see that there we have two Weil groups. So there is W, which is the Weil group of J. Okay, and there is WM, which is the Weil group of M mu. And then I have some set which is MW, and which is inside W, and which is a representative of the cosets. So it represents the W divided by MW. Okay, so this is the constant representative. Okay. Okay, and then I have a length function, just as before, from MW to 0D, where this is the dimension of the Shimura variety. All right. Okay, so now with all this data, I claim that there is a complex. Sorry, excuse me. No, I need one more assumption that. Sorry, I will also assume from now that Kp, so my level at P, is an E-word. Okay, we could work with any group with an E-word decomposition, but let's assume that it's an E-word. Okay. All right, so now what I claim is that in this setting, there, okay, cousin, so which depends on the time level, Kp, and which depends on the weight, kappa. Okay, this is really a kappa. Okay, and so this complex has the following shape. So there is first some A0 identity, Kp, kappa, finite slope. Then the sum for all the W in MW of the H1. Sorry, so the terms of the complex are indexed by the elements of MW, and then they are in degree according to the length. Okay. And then I have some space here that I'm going to define, and so on. Okay. And so this goes from degree 0 to degree D. Okay, so now, okay, and there are also like cuspidal and interior versions of this. Right. And so now the claim, so it's the following theorem. I mean, the theorem is empty for the moment because I've not really told you what is this complex. But anyway, the theorem is that if you look at the interior cohomology of the Shimura variety in weight kappa, so then this group is a subquotient. The subquotient of the cohomology of the Cousin complex. Right? So the situation is not exactly as good as for flag varieties, but I mean, we have at least some control, okay? So I should remark that we actually conjecture that this is an isomorphism if the Shimura variety is compact. Okay, and well, we can prove it in dimension less than. Okay, all right. So now I think I should tell you. I mean, I should tell you of some examples, maybe, but let me check also the time. Sorry, I need to check the time. Okay, that's fine. Okay, it's okay. Okay. So. Okay, so now, yeah, I should tell you a little bit how this looks like. Okay, so maybe yes. So what are these cohomologies? So what are these cohomologies? Hi, double. Okay, so these are some. So first, I mean, just as before, these are QP vector spaces of infinite dimension. Okay, so these are huge spaces. I mean, these are actually limits of planar spaces, but of infinite dimension. Okay, so oh no, sorry, no, but they are infinite dimension, right? Sorry, and there is. Sorry, I think there should be a subscript finite slope part. Yes, exactly. So this, yeah. So the second thing is how are they obtained? Well, they are the finite slope part of some local cohomology on the Shimura variety. So it's some cohomology we support in certain regions of the Shimura variety, but this I'm going to describe in a moment. And just as before, I mean, just as in the case of the flag variety, we have estimates of slopes. Okay, so remember, in the case of the flag variety, we had estimates for the weights of T, and there we have estimates for the slopes. All right. So now I should tell you, where does the support condition come from? And really, well, the support condition is in general a bit, I mean, it's a bit involved to define it, but let me try to explain. So we have this flag variety, G divided by P mu. So, okay, by flag G mu. Okay, and there is a perfectoid space, which is the limit over all level at P of the Shimura variety. Okay, I mean, that was first constructed by Scholz and then defined by other people. But okay, and very important, there is some Hochstate period map there. Okay, that was also constructed by Scholz and then Kareni Scholz, so to the flag variety. So we have this Hochstate period map there, and then we have like our finite level Shimura variety. Okay, the one we are working with, and then if you want, there is some like some truncated in some sense Hochstate period. Sorry, I mean, so I should say that the first period map is really a map of adic spaces. Okay, and the second one, I just view it as a map of topological spaces. Okay, I'm not trying to give any structure to this flag G mu divided by Kp. Okay, I don't really care. All right, so we have some diagram like this, and so you see, well, first observe that so flag G mu has a stratification, which is indeed indexed by the set MW, which seems to play an important role. Right. So the other thing is that by so I mean, why? Well, so we can view MW as for the action of the torus on the flag G mu, okay, which somehow explain why they show up in this case. So we also know that so if you take some W, so now I mean I can identify W also as, yes, by this last formula I can identify W with points in the flag variety. And so if I take a point like this in the flag variety, then by Scholze-Weinstein, I can somehow view it as a p-divisible group, plus some structure, plus some extra structure, roughly. I mean, like this is literally true, maybe in the Ziegel case or in Hodge case, and then it's more involved in the abelian case. Right? And then what's like P Hochstate minus 1 of W, then this is some Igusa variety by Kareni Scholz. Okay, so it's some perfectoid Igusa variety. So it means that you're parametrizing, let's say, abelian schemes with extra structure, and you fixed the isomorphism class of, I mean, you fixed the p-divisible group. Igusa variety. Okay, and so these cohomologies now, they are somehow finite slope, they are finite slope part of cohomology of some neighborhood of this particular Igusa variety. Okay, so I mean there are lots of Igusa varieties in the Shimura variety. I mean that are parameterized by the point of flag G mu, and then I somehow pick just finite number of them, and this complex is just constructed out of these neighborhoods of this Igusa variety. Okay, okay, and there's, I mean it's not only the cohomology of a neighborhood, but there is a support condition. But this is a bit tricky to precisely discuss. So let me give some example. Right, because I mean, in some cases, this doesn't need all this to be defined. So let's do GL2. So if we do GL2, then we are speaking of some modular curve X naught of P. And then I claim that if I take some weight, K in Z, then this now something familiar. So the A0 will just be, you take the space of over convergent modular forms of weight K, you take the finite slope part. And then there's a boundary map to a space which is, say, the H1 with compact support of the dagger space ordinary locus with value in the same sheaf. And you take the finite slope part. Okay? So yeah, it does not really need to be, I mean, yeah, you can define it. You don't need anything about this Hochstedt period map. So let me just say that in this case, one, so the identity element in W, which is MW, this really corresponds to the following P divisible group. So the ordinary one, QP plus, sorry, μP, together with the level structure given by the group μP, okay? And the other element, so the non-trivial element, it corresponds to the same P divisible group, but now you take the étale level structure. Okay, so in this case, there's, I mean, somehow the finite slope, I mean, this Cousin complex, it only takes care about like the ordinary locus and the neighborhoods of the ordinary locus. Okay. All right. Let me also, okay, so let me, I mean, I'm probably now running seriously out of time. Let's see. No, it's still okay. So now I can also say something about, I mean, just for the future, I can just say that, right, so last time, I mean, when we looked at the cohomology of the flag variety, it was quite important that somehow we had this Cousin complex and we realized that the weights for the torus, they're on, I mean, on each of the terms of this Cousin complex, okay? So here, the same thing happens with the UP operator, okay? In the sense that now you have a UP action on this, so UP acts, okay? And you can bound the slopes. So, I mean, I'm going to take some slightly non-standard normalization of the UP operator, but let's say that the slopes on the first term are greater than 1, okay? And then the slopes on the second, so on the complex in degree 1, the second complex are greater than K. Okay, so this is something that you can prove. And so you again see like a similar behavior that somehow the slopes are not like, I mean, there's a different slope behavior according to the term, to the module that you look in the Cousin complex. All right, so let me maybe briefly give a second example where now things become a little bit more interesting. So now let me look at GL2 over F, where now F over Q has degree 2, so it's, I mean, it's totally real. Totally real, degree 2. Okay, and let me assume that P is maybe inert. Okay, so it's more interesting in this case. Then the Cousin complex looks, so now it has two, I mean, it's a length 2 complex, right? So there is A01. So let me not write anything, but just to save a bit of notation. Right, so sorry. Yeah, I should say that now the Weil group, which is also MW, because the Levy is a torus. And now it's the product of two copies of the Weil group for GL2 over Q, right? I mean, I'm always looking at the geometric Weil group, right? So, right, so now I have H1, H01. Then in degree 1, I have two terms, which are H01 cross W. Sorry, I should just write like this. So I have some H01 cross W. Sorry, I have some H1 cross W plus some H1 W cross 1. And then I have H2 W cross W. Okay, so it looks like this, the complex. Right, so now, I mean, so now these two elements, 1 and W cross W, they correspond to the ordinary P divisible groups. So they correspond to mu P infinity plus QP over ZP tensor with OF. Okay. okay, and then you have two possible level structure, and this gives the one or the W cross W. And so these two cohomologies, I mean, so the first guy is just the overconvergent cohomology in weight kappa. Okay, so and the last guy is just like the compactly supported cohomology of the ordinary locus. I mean, or viewed as the dagger space in weight kappa. But then you have these two middle guys, and so these two middle guys, they now correspond to non-ordinary p-divisible group. And what is this group? This is the Lubin-Tate for OF plus the Lubin-Tate dual for F. So you have two Lubin-Tate groups because you have, I mean, yeah, there are two Lubin-Tate groups. Okay. I mean, you have two embeddings of F, or sorry, of FP, I mean, I should say OFP. You have two embeddings of OFP into Q. Okay. And so you get two Lubin-Tate groups, which are Lubin-Tate, I mean, choose one, and then you have the dual, which is the other. All right. Okay, and then you have two level structure. Okay, very, very good. Okay, so now I can move next to the application. So this is the last part of it. Okay, so I mean, George will speak about more applications. So I will speak about its application 1, and this is an application to proving vanishing theorems. Okay, so just like what we saw at the very beginning, like we could use the Cousin complex to prove vanishing theorems for the flag variety. And there we can also use it. So I should say it's a general fact. It's a general that we can bound slopes on the Cousin complex. Okay, just what we saw for the, I mean, the case of the modular curve, there's something quite general actually. Okay, and so using this, you deduce quite easily. I mean, you just somehow, yeah. So you deduce this. So let's just as before introduce a set which is C of kappa. So I have my weight, and then I consider C of kappa, which Weil group elements such that W minus 1, W0 M kappa plus rho is anti-dominant. So, I mean, it's just a set that, right, records, sorry, plus rho is anti-dominant, right? So it's just a set that records somehow the position of kappa in the white space. And basically, the set C of kappa, okay, I'll make a remark after, but okay, anyway. Okay, and so we have this set which remembers the position, and then we can look at the interior cohomology in weight kappa, and then we take the small slope part. Okay, so I've not defined, I mean, I'm not going to define it. It's a bit combinatorial, but I should the best possible notion of small slope part. Okay. So somehow, I mean, for modular curves, it would be weight, it would be slope strictly less than k minus 1 if k is strictly, I mean, it's greater than 1, and slope strictly less than 1 minus k if k is negative. Okay, and it's, I mean, right? And so this small slope part is in degree. It's concentrated in degree. So just as before, you take the nth of the length, and you take the max of the length of W, where W belongs to this set. C of kappa. Right? So, okay. So before I just make a quick comment, and probably I finish there. Let me say that from a theorem concerning the interior cohomology of a Q-local system. So now if you take the Betti cohomology of the Shimura variety with value in W, where W is a Q local system, and then if you apply the small slope part, then this is in the middle degree. Okay, so the relation between these two theorems is Falting's BGG resolution, or spectral sequence. Okay, so let me just check one more time the time. Okay, no, it's very good. Okay. Okay, so Okay, so let me make one remark and maybe one picture about the meaning of this C of kappa. So the first thing I should say, the first should say is that C of kappa, this has cardinality 1 if and only if kappa is J regular. Sorry, if kappa plus rho is J regular. Okay, so the thing you see is that kappa plus rho is the infinitesimal character, so therefore it's basically the Dirichlet weights of the, of the Galois representation that should exist. Okay, and so you find there this phenomena that somehow if the Dirichlet weights are regular, then there should be cohomology in only 1 degree. Okay, and then if the Dirichlet weights are irregular, then the more irregular they are, the more spread of cohomology you get. Okay, so it's confirmed by this result. Okay, I should make a second. So maybe let me label the theorem. So there will be theorem A and theorem B. So I would like to say that theorem A is an analog of an Archimedean theorem of Harris, the Blasius, Harris, Ramakrishnan, Williams, Schmidt, Mirkovich. Okay, and so this Archimedean theorem, it says that somehow the tempered at infinity interior cohomology. So if you okay, with weight some nu kappa. Okay, and then if you take the part of the cohomology with tempered at infinity, which is some Archimedean condition, then it has the same vanishing, so the same concentration result. Okay, so it's exactly the same result, but the assumption is different, right? Because we are making some assumption at P, which is having small slope, which is a condition at P, and they are making some assumption at infinity, but they get the same concentration result. So maybe we can think of small slope is some p-adic. P-adic in the sense of p-adic analysis is some p-adic version. That's maybe one way to. Okay, so okay, I should also say that, of course, that theorem B, is, of course, there is the work of Karajan and Scholze. Okay, and so they prove some concentration result in the middle degree, but they use the genericity assumption, which is again different from some small slope. Okay, using genericity. Okay, and of course so it's a different assumption, but the result is much better in the sense that it also works with torsion coefficients. Okay, and for the moment we cannot work with torsion coefficient, but maybe one. Okay. Yes, I still have one or two. So let me finish by drawing a picture. Okay, so let me draw a picture. Okay, for GSP4, so that you see what we found. So you see, so for GSP4, so the weight space is kind of two-dimensional. Okay, so sheaf, you have K1, K2, and let me just write that this sheaf nu K1, K2 will just be, and probably you know the meaning. It's kind of a standard notation. Okay, so I take sim K1 minus K2 tensor det K2 of the conormal sheaf of the universal abelian variety. Okay, and so we can draw a picture like this, right? So this is so this will be a picture of my weight space. Okay, so K1, K2. Okay, and then I have some lines to draw there. So I'm drawing some translation of the, okay. Yeah, I'm drawing some translation of the chambers by row. Okay. And this is, okay. So I have some lines. So this is K2 equal 2. This is K1 plus K2 equal 3. And this is K1 equal 1. Okay. And so, I mean, this is the forbidden region, okay, because here the weight is not mu dominant. Okay, and so there's, I mean, you don't look at these weights. Okay, so the mu dominant weights are there. Okay, and so now somehow this is the H0 region, like in some ideal world, this is the region of the weight space. You should have only H0. Now on this wall you should have H0 and H1. Then this is the region where you should have H1. Then on this wall you should have H1 and H2. Then this is the region where you should have H2. Then on the wall there, you should have H2 and H3. And there you should have H3, okay? And so, I mean, this is not literally true, right? So, I mean, it's not true without making any operation. It's not true that the interior cohomology satisfies this concentration result. There are counterexamples. But so what I'm telling you is that if you take the small slope part, then it's at okay, and so in particular, all the ordinary cohomology is small slope and it satisfies this vanishing. Okay, and so I think I should stop here. Is that right?
Yes, thank you so much, Vincent, for very inspiring talk. Actually, thank you so much. Everyone, let's have a show of appreciation if anyone interested. I'm trying myself to get to this reaction button. And everyone wishing to ask a question, if you can please, using one of those reaction buttons, raise your hand so I can see you and give you permission to ask the question. Namely, to unmute you. Okay, I see Yi Chao. Yeah, I'm asking you to unmute now. Hope it works. Yes, go ahead, please.
Okay, so I would like to ask you if the condition on your first validation result is optimal. That means the inf of LW and the super
yes.
W is optimal.
Yeah, I think, I mean, so just to tell you, yeah, I think it's optimal, for example, in, yes, so for example, I mean, yes, for example, in the Hilbert case.
Mm-hmm. Okay.
Yeah, I mean, you know, I mean, when we proved this control theorem, so some time ago, we had some non-optimal bound, and then with Xiao, you found an optimal bound. Is that right?
Mm-hmm.
Well, then our small slope condition is your small slope condition.
Oh, I see.
So it's the optimal bound. Yes.
Ah, you mean the slope condition? I mean the degree condition, the range.
Ah, no, sorry.
Is the range condition optimal?
The rank?
Range.
The range.
You that the interior cohomology constituted in range.
Yeah. No. Yes, the range is optimal, but I mean, yes, the range is optimal and the condition is optimal.
Okay, thank you.
No, but I just want to clarify this that there are several notions of small slope, and I think we're really using the natural one. Yes.
Okay, thank you.
There was a question from David Leffler. David, please go ahead.
Well, it was actually a question from me.
Okay.
Hi, Sarah.
So can you also vary the weights?
Yeah, but this is the next talk. So the next talk will be great, actually. So no, but yes. So George in the next talk will in particular explain how to vary the weight in the Cousin complex.
Excellent.
Yes.
Thank you.
Yes.
If I could ask a question as well.
Yes.
The perfectoid, you mentioned the perfectoid Shimura variety with toroidal compactification.
Yes.
And I didn't know you could do this. I mean, there's in the Cariani-Scholzer, they use the minimal compactification.
Yeah, it's true. But then Kai Wen wrote a paper, I mean, at least in the Hodge case, Kai Wen proved that you can choose the cone decomposition in such a way that you get a closed embedding into a Siegel-Shimoda variety. And we know that the toroidal compactification of Siegel-Shimoda variety is perfectoid at infinite level. And therefore, since we really have, I mean, in that case, we really have a closed embedding, which is not the case. I mean, you know this, right? Yeah. So yeah. But just, I mean, I should say that we don't really use that the Shimoda variety at infinite level is perfectoid. I want to say that, I mean, we don't use it crucially. I mean, yeah, I think we don't. I mean, what we use crucially is the affineness of the Hodge state period map, but which is something that can be formulated also at a finite level, right? And this is really crucial, the affineness of the Hodge state period map. Yes.
Okay, David. Okay, so there's a question from Gauthier Ponsinet. Please go ahead.
Hi, Gauthier.
Yeah. Yes, small question because the connection cost. I lost the connection.
Oh.
Well, in your first theorem, after you have a conjecture about the fact that the cohomology of the Cousin complex is the same as the integral cohomology, and you said that you checked this in some case, but I didn't hear when you checked.
No, just so conjecture is the same thing for compact Shimoda varieties, and in that case, there's only one cohomology, and yeah, we can prove this for in dimension less than 2, so for surfaces.
Okay.
Yes.
Okay. Right. That's it. Thank you.
And there's a follow-up question from Yichao Tian. Yichao, please.
No, I don't have further questions. Sorry. Maybe misunderstood.
Well, since you're on the air, okay. So are there any other questions or comments?
So let me also say that I promise we are writing the paper and it will soon be available. Yeah, but I've promised this to many people, and I've not followed. I mean, I've not fulfilled the deadlines, but it's on the way. Really, promise.
So if there are no more questions, I guess we can, well, first clap our hands again for Vincent.